This is the first of a series of 3 videos in which I will explain how to calculate the area under a curve. You should know how to integrate simple functions and the difference between definite and indefinite integration. In this video I will explain the theory and do a simple example. At the end, a question for you to attempt will be displayed. Pause the video at that point, attempt the problem, and then resume the video for a worked solution. The 2 subsequent videos will have more difficult examples. So let's consider the area under the curve y equals x squared plus 1, and above the x-axis here and between the line x equals 1 and x equals 3. So we have this area here that we're going to try and calculate. We divide up the area into a number of strips of equal width. Here I've got 5 strips, but I can increase that and have many more strips, but of smaller width. To calculate the area, I could approximate the strips as rectangles of the same width, but of the height of the y value of at the front end of each rectangle. We can see if I do that, then the total area of the rectangles is less than the area under the curve, because we're missing these pieces here. However, if I increase the number of strips, I increase the number of rectangles, and we can see the area becomes much closer to the area under the curve. As we can see, we start with 1 strip, the area is 4, and as I increase the number of strips, the area also increases, and as we keep increasing it, as you say, the area is around about 10.4. You can try this yourself if you go into the demonstration on the course in Study Smart, and if you can see, you can click on the areas here, we turn them black, and you see this small icon here which is yellow and looks like a piece of lightning. Then if you click on that, this box appears, and then you can change the number of rectangles, number of strips. This gives you the you can see how the more strips you have, the better is the approximation. So let us divide the area under the curve y equals x squared plus 1 into some strips. Each strip has width delta x, height y, and if A is the area under the curve up until the point x here, then the area of the strip we can call delta A, the change in area. So approximating the area of the strip delta A as a rectangle like that, the area of the strip delta A is approximately the area of the rectangle, which is y delta x, and dividing by delta x, we have delta A divided by delta x is approximately equal to y. And as we increase the number of strips and decrease the value of delta x, we'll let delta x tends to 0, and as we know with differentiation, delta a over delta x becomes dA by dx, and dA by dx will then equal y. So what we have here is the derivative of the area is y. And as integration is the reverse of differentiation, we have a equals the integral of y dx. But a is also the sum of all of the strips, the areas of the strips, as x goes from 1 to 3. So we have the sum of the areas is the integral of y dx, and integration is sum. Now, for y equals x squared plus 1, if we integrate y dx, we get the integral of x squared plus 1 dx, and integrating x squared becomes x cubed over 3, and 1 becomes x, and then we have to add the arbitrary constant c. So we can say the area is the area up to a point x from an arbitrary point which can be down here somewhere. Now if we substitute the value 1 for x, so if x equals 1, then the area, we'll say x is 1, would be 1/3 plus 1 plus c, which is 4/3 plus c, and that's the area up till 1, which can be this area here from some arbitrary value over here. And if we substitute x equals 3, we can have the area at 3, which equals 3 cubed 27 over 3 plus 3 plus c, which is 9 plus 3, which is 12 plus c. And this can represent the area from the arbitrary point here to the point where x equals 3. And so we can see that the area required, which is this area here, is A3 minus A1, the green bit minus the yellow bit. And so we have the area that we want is A3 minus A1, which is 12 plus c minus 4/3 plus c, and as we can see the c's will cancel out, so we have 12 minus 4/3, 32 divided by 3. So A3 minus A1 is the difference of the values of the integral when x is 3 and x is 1. And as we know, we write that as the definite integral between 3 and 1 of x squared plus 1 dx. And so we find that area is the definite integral between the two values. So in general, the area between the x-axis, the curve y equals f of x and the lines x equals a and x equals b is given by the integral of f of x dx between the limits of a and b. So for example, find the area enclosed by the x-axis and the curve given by the equation y equals x minus 1 multiplied by 4 minus x. Now, the best thing to do here, first of all, is to sketch the curve. We'll expand the brackets, so we have y equals, we have minus x squared, we have 4x plus x, which gives 5x, and we have minus 1 times 4, which is minus 4. This tells us it's a quadratic. The coefficient of x squared is negative, and so it has a maximum. And we can see from the original equation that it crosses the x-axis with x equals 1 and x equals 4. And from this equation, the expanded equation, it crosses the y-axis when y is minus 4. And so the curve looks like that. And this is 1, and this is 4, and this is minus 4. So the required area is the area under the curve and above the x-axis, like that. And so the area equals the integral between the limits 1 and 4 of y dx, which is the integral between 1 and 4 of minus x squared plus 5x minus 4 dx. So a equals, we integrate that, minus x squared is minus x cubed over 3, 5x is 5x squared over 2, minus 4x, between the limits of 1 and 4. So we substitute in 4 as x, so that would be minus 64 over 3 plus 5 times 16 over 2, which is 80 over 2, so that's 40, and minus 4 times 4 is 16, and then subtract what we get when we substitute in 1, so we have minus a third plus 5 over 2 minus 4, and this equals 8 over 3 minus 11 over 6, which is 8 over 3 plus 11 over 6, which is 27 over 6, which is 9 over 2, and that's the required area, 9 over 2, and we'll have square units. Whatever the units were, it's square units. Now you might like to pause this video and try these two problems yourself. Okay, the first problem then, find the area bounded by the x-axis, the curve y equals 4x cubed, and the lines x equals 1 and x equals 3. First of all, sketch the curve. This is a cubic, 4x cubed. It's a simple cubic, like that. And we want to find the area between x is 1 and x is 3. So this is this area here. So a is equal to the integral between 1 and 3 of 4x cubed dx. And we integrate 4x cubed integrates to x to the power of 4 over 4. So multiplied by 4 gives us x to the power of 4 between 1 and 3, and so we'll substitute in x equals 3, gives us 3 to the power of 4, which is 81, and substitute in 1, which gives us 1, so the answer is 80 square units. The second problem, find the area bounded by y equals x into 2 minus x and the x-axis. We sketch the curve. Again, if we expand the bracket here, we have 2x minus x squared. Again, the negative x squared would mean a maximum value, and we can see that the curve passes through 0, x is 0, the origin, and x is 2, and so it will look like that, and this here is the required area. And so the area A is the integral between the origin, so x is 0, and the point where it crosses the x-axis, which is x is 2. So that is the integral of 2x minus x squared dx between 0 and 2, which is equal to, which is x squared minus x cubed over 3 between the limits of 0 and 2, which, substituting in 2, gives us 4 minus 8 thirds. Substitute 0, we get 0. And so 4 minus 8 thirds is 12 minus 8 over 3, which is 4 over 3 square units. This is the end of the first video on area under a curve. In the second video, we will investigate what happens when some or all of the area is below the x-axis.